So before I jump to these slides, now we're going to talk a bit more in practical terms about experiments. So we now know conceptually that they are a very powerful research design to answer total effects. And in combination with some modeling, they can be very powerful to also test, get to structural parameters, okay? Let me, but I don't want you to go with the impression that because even if you don't want to go very structural and you do an experiment and you get some like total effect, it doesn't have to necessarily be a policy parameter. You can test theories, and that's very useful with experiments. So let me just tell you an experiment I did, which I really like it. I don't have the slides, unfortunately, because I know it was mostly education, but someone mentioned yesterday that works on prices in the retail industry. I think it was here, right? So I'd like to talk to you about this later. But so essentially, one big question is what's the effect of competition, right, on prices? And so most of the research will compare markets where there are more supply. Like a lot of recent research in this area is, for example, what's the effect of the entry of Walmart on the prices of competitors, things like that. And quality is a big issue. So, for example, this paper in the QJE that shows that when Walmart enters, essentially that led to an increase in the inventories of all the other stores, which is a kind of measure of quality, because the worst can happen to customers, go to a shop, not find what they're looking for, and then whatever. So, but there's not been experimental research in this area, because you see, right, randomizing the number of stores in a market is beyond what can we think of. Oh, maybe no. So it turns out that I found a way to do it, obviously in a specific context, and that's related to this. It's not going to be informative to all possible ways of think about competition and in every possible market, but it's very interesting what we did and the results we find. The context is food retail stores for the poor in a poor country. So the country is Dominican Republic, and essentially the government has a program to assist the poor. It's very common programs which are called conditional cash transfers. So the government transfers money to the poor has to do something. Normally they have to send the child to school, things like that. But this particular case, it was different. The government, but then the families could do whatever they want with the money. Now, in this program, the government transfer the money to the poor, but the poor can only use that money to buy food in certain stores. And for that, the store has to be affiliated to a network where essentially they have some machines where they can read the cards of the poor to know the balance and then subtract the money from the balance, okay? So, well, the government did the program, whatever they were the stores, kind of 4 or 5 stores on average per market. But over time, the program grew, so they incorporated more families. And the government believed that the store had some market power, which kind of in a way it's true, because people were only going to one store, and they have some maybe market power to charge higher prices. So the government want to expand the numbers of stores, and we convince them to randomize that. To randomize, we don't remember the numbers, but let's say 70-something markets, randomize 0 new store, 1 new store, 2 new stores, 3 new stores, okay? And so we collect data on prices and quality before the experiment took place and after, 6 months after. And obviously, it was very tricky to measure prices, because it's not like you have scam prices for everything like in the US, so you have to still go to the stores and ask the price for every good, and they could lie or whatever. And so what we did was to do that. We went to all the stores and collect prices, but we also took a random sample of 30 beneficiaries in each market, and we also asked them the amount they spent and how much they got, so we could get the unit price they pay. Very interesting. We got very reliable data on prices, so the correlation is extremely high. But also we can estimate the effect of competition on prices by using the price that we got from the stores, or the average price we got for the 30 consumers, and we get the same effects. Not exactly, but like if we find like a 6% decrease in prices in one case, a 4% decrease in prices, they're not statistically different. So that will be, and we didn't find much effect on quality, although then I'm revising them, because essentially quality, a lot of quality is measured by price, right? So it gets a bit tricky. Most of the quality of going to the retail has to do with the experience. So we want to separate the price from the experience. So it turns out that we find that an increase in quality by the self-report experience. But then we don't find any objective measure to back up that. So it might be that it's something unobservable, so we are maybe agnostic in that, but that is just to say that, sometimes you can find ways to do experiments about testing important theoretical predictions in ways that are not conventional. That maybe is the way to put it. Good. But then context matter a lot, right? So in a way, that's why it's related to this. So the fact that, suppose we take the results, and suppose just for the seminar, we get that the result is that once you have entry of new firms in the market, prices on average goes down 6%, quality doesn't improve much. That doesn't mean that competition cannot improve quality in other setups, right? In other markets, among other populations. So maybe this very poor population buying, at the end they buy this food only, and maybe there's not much scope for quality to go up. But if you do an experiment on competition in the airline industry, quality is going to be everything. So that goes to the issue of internal validity with external validity. And context matter also, because you could have told me, well, but it's competition for the voucher money, not for all expenses, right? So when the poor go to those stores, they buy more than the voucher. The voucher is only part of the expenses. But then, yeah, in the paper we provide context of how much they spend and whether they go to different stores or not to spend the whole money. So a lot of the context is in every experiment is really important to be provided because it's the only way we can start to build knowledge going from not only one study but from a set studies to get external validity. So it's often the case, you read, that in economics there's not that many cases where you have exactly the same experiment done many times as to know it, but in psychology it's often the case that you read, yeah, this very exciting experiment, and then they can never replicate it, right? I might be exaggerating, but that's something you hear all the time. And that's not really very useful if that's true, right? And so one thing that I did a couple of times now, and I find very interesting, is I did the same experiment in different populations, right? So I have a housing experiment. I did it in 3 countries, the same, exactly the same. And so by doing that, within a paper, I start to move from internal validity to external validity. But even when you do exactly the same experiment, right, which is to extremely poor families, we went with an NGO to slums, and essentially they build a house, which is just 1 room, right? It's not more than that, to the poor, and that's a huge improvement and it's the same house in the 3 countries. It turns out that even if you do the same house in 3 countries, it's not the same intervention, because the counterfactual is different. So in one country, they were relatively poorer. So in terms of the counterfactual, the effects is different. Fortunately, in the paper, we find something very nice, which is for the variables, we find a positive effect. We find it in the 3 countries. For the variable, we find nothing. We find nothing everywhere. And for the country that it was poorer and we find positive effect, the effect is larger, which makes sense because the intervention was relatively larger, okay? And that's a way to build this external validity. Obviously, it's expensive, right? I'm not saying, it's not free lunch, remember that. And someone will judge, and there are criticisms about experiments and about the cost, and it's all points that are well taken, and we keep thinking about these issues. Now that in a way I talk about instrumental variables, I get back to something I did again to build external validity in a now zero cost environment. Good. So the basic design of an experiment is very simple. I just want to talk a bit about this. You randomize among hopefully a population, but obviously it's a sample, but hopefully it's representative of a population. It's not, then the issue of external validity gets more pressing. And you randomize to a treatment and a control group. And then you don't need any data. Strictly speaking, in a large sample, you don't need any data before the experiment, because you know that if randomization was physically executed in a large sample, the groups will be probabilistically the same. Okay. Often people do, and then you just compare the outcomes after, and you basically identify the average treatment effect on this sample. And again, whether it can be extrapolated to the population or not depends on whether it's random. It doesn't have to be only one treatment group. then you can have more than one treatment group. And then let me give you an advice that a lot of my colleagues will maybe not like it, my advice, but this thing, do a KISS randomization. And that means keep it simple. It's very easy to start thinking, oh, given that I'm going to go to the field, collect data, let's have 40 hypotheses, 10 treatments, and all that. The problem is then you don't have statistical power. And you have to think why you are doing this. So suppose you have 2 treatments, right? Treatment 1, treatment 2, and a control group. You will compare treatment 1 to the control group. And maybe you want to detect an effect of 10% increase in an outcome. And then for that you need 2,000 families. And then you think that treatment 2 is more powerful, and you will detect an effect of 15%. And then you need 800 families. So then you say, well, sample size of 1,000 will allow me to detect the effect of treatment 1, and it will more than allow me to detect the effect of treatment 2 with a given power, let's say a power of 90% at a significant level of 5%. But the interesting thing will be to really show that treatment 2 is more powerful than treatment 1, and there you need to detect an effect of 5%. You need to be consistent. You say 1 was 10, the other was 15, now it's 5. You need 4,000 households. So the more hypotheses you have, the larger and larger are the sample size. And unfortunately, there's a lot of experiments. They have many, many arms and are not well powered. And then the risk of that is that you end up just concluding that the most effective arm of the experiment was the one in which by random variability you got some large effects because you got small cells, right? That's not, it's better to be cautious and say, I'm just going to learn only about these 1 or 2 treatments, but you can see 4 or 5 treatments, which I'm not that sympathetic to. At least you have a huge possibility of a huge budget to have a very large sample size. But often the problem with the sample size is not only your budget, it's the availability of units for the randomization, okay? So for example, someone asked me about lab experiments. I don't do a lot of them, but I do some. Mostly are extremely theoretically driven, right? When I go to the lab, I see most of, not as really a test, most of, if it doesn't work in the lab, there's no hope, right? And that's it. And so when I go to lab, it's extremely theoretically driven. It's just testing specific effects of specific models. So I'm working on a collective action, very general model that is very nice because it allows to really predict exactly what people will play, mapping from initial beliefs to what they will cooperate or not, depending on parameters. And I forgot what I'm talking about this. All right, but I need at least 20 subjects in every game. It's a nightmare. It's a nightmare. It's having to get 20 kids to really show up. I was doing it. Now I'm thinking to move it to China, where I hope there's 20 is a small number there. I'm affiliated with a lab in China, so okay. So most often the design will essentially look at the outcomes before and after, but the outcomes before are only relevant to just check what you already know, that essentially randomization was effective in balancing the group. You don't want to do panel data because you have the initial outcomes, right? That's, in a way, it could be a big mistake. And a big mistake that often happens is that when one of the outcomes was unbalanced, right? A lot of people turn to panel data, say, oh, okay, the outcome was unbalanced, I do panel data. That could be really bad compared to just ignore the fact that it was unbalanced. I'm going to get back into a concrete example. This is something that is counterintuitive. It's very counterintuitive. I'll get back to that in a second. And often that will be ideal to have more than one observation before. If essentially you plan for some reason to use the panel data, but this, as I say, if randomization was effective, you don't need it. So yeah, I actually don't know why I have this slide here. Okay, so fine. Suppose you don't have an experiment and you are not able to claim ignorability of treatment or ignorability of the causing force. How do you deal with endogeneity? Right? There's two basic ways. One is instrumental variables and the other is panel data. Let's talk about instrumental variables in a very simple context. The context we had before is the context of where essentially we want to estimate the rate of return to education or whatever, beta, let's say. I mean, it's called often the rate of return to education, but that's not exactly true. Needs a lot of assumptions about stationarity that are not necessarily true. And then we have ability in the error term, and now remember that ability was a function of education, so education is correlated with the error term U. And so we cannot estimate that equation by OLS. What is an instrumental variable? An instrumental variable is a variable that satisfies two conditions. Okay, this is like very simple in conceptual terms, very subtle in practical terms. In conceptual terms, you need a variable set that satisfies the following. It is correlated with S. Right? In another way, it has something to say about X. So let me let me use this for that. Okay? So everyone sees this, right? So think this is the variability of Y. Right? That's the variability of Y, the dependent variable. This is the variability of S. And this is the variability of ability. Right? So, you know, if ability is observed, we said it before, then there's no problem, right? Well, OLS works and Y works, because OLS, to estimate beta, use only this covariability. That's beta. Why OLS use this covariability? Because you say, well, here I know that Y and S covary, and nothing else covary with Y. So that I can attribute to S. That's what OLS has. To estimate rho, the OLS use this. This is rho. That the same happened. It's only attributed, right? So OLS doesn't use this covariability because it doesn't know what part it has to be attributed to S and what part it has to be attributed to A. Contrary to the bad name OLS gain, OLS is extremely smart when everything is observed. The problem is that when you don't observe A, what the OLS will do and why it doesn't work? It will say, oh, this is also beta, right? All that variability will be attributed to beta. So that's why essentially you get an inconsistent estimator. Now, what an instrumental variable is? An instrumental variable is a variable, right, that is correlated with S, set. So for example, is this variable, set. It's correlated with S, and it's not correlated with Y in any other way that's through S. Why you need those two conditions? Because if you satisfy those two conditions, that is correlated with S, and is correlated with S only through S, then what the instrumental variable is going to do is to use this covariability, and only this covariability, to estimate beta. And then it's fine. That's covariability. It's only the covariability between S and wages, and identifies beta. What's the problem is that it's very imprecise, right? Because compared to OLS, because before OLS will have used, well, all, and it will be inconsistent, and if A were present, it will have used all this covariability. Now you use this. Suppose you get an instrument now that only use this covariability. Well, it's only using this. Still is consistent when n goes to infinity, but in your sample, right, it could be extremely imprecise. Okay? So okay, then condition 1, covariance of set and S is different of 0. It means that set and S have covariability. The second condition is that the covariability of set and the error term has to be 0. It means that set only affects Y through S, because if set affects Y also through other channels, for example through A, then you still will confound part of the effect of S with the effect on A, and you didn't solve the problem, right? So when you have an instrument, again, you have to see about the whole process that generates the data, because there's no other way to discuss the validity of the instrument, because one condition, the covariance of set and S, is observable. That you can test, whether it's in the data or not. There's no problem. The problem is you never can test the covariance of set and U, because again, the only thing you will have is the estimated error term. And by construction, that's going to be 0. That's exactly what the instrumental variable will do. But that's not the true error term, so there's no way to test it. I know you want to ask me a question, and I want to finish my sentence first. So at the end of the day, like in every time you make an assumption for identification, right? Remember what I said before the break. If you randomize, you know that treatment is independent of the error term, of the potential outcomes, or you could make that as an assumption. Well, it's an assumption, you will go and fight, and defend it or not, you will provide ancillary data. In instrumental variables, it's going to be the same, but instead of you trying to show that X is exogenous, now you are trying to show that Z is exogenous. Yeah.
Yeah, I'm wondering about the difference. What is the difference between endogeneity in your which you explained, and multicollinearity between the two independent variables?
Right. The difference is conceptually the difference is like, you know, night and day, something like that. But there is so what is multicollinearity? Multicollinearity means that essentially you have these two regressors, right, A and S, and in your sample they have some linear correlation, like you can predict one with the other, right? And that we claim that that's the case, right? But multicollinearity is not a problem in the sense that it affects the precision of your estimators, but that's only in a small samples issue, right? Asymptotically, it's not a problem. Right? Multicollinearity is not a problem asymptotically. Think about that. You're never gonna try to separate the effect of S and A if they are perfectly collinear in the population, because there's no way to separate them, right?
But in OLS we assume that there is
What?
In OLS we assume that there is zero multicollinearity between the.
I don't understand. Sorry.
In OLS, we assume that there is no multicollinearity between the. We take care that there won't be a multicollinearity between the two or more
Right. Okay.
regressors.
Right. I'm trying to demystify that. There were in the old times one of the conditions people write down is variables don't have to be collinear, and yes, in the population they don't have to be collinear, right? But what I'm saying is that fine in the population, but what does it mean that A and S in the population are perfectly collinear? Perfectly collinear. It means that they exactly move one with the other linearly. And if that's the case, it will be nonsense to write down a model where you try to separate them. So in practical terms, it's only a sample problem, the collinearity, right? Just in your sample, it might be more collinearity than in another sample, but there's not going to be perfectly collinearity, okay? All right, so that's, so finding an instrument, the problem is where presented like this is very simple, right? Think about instrumental variables is, okay, I would like to claim that S is exogenous. If it's X is exogenous, I identify the model through the moment condition that the covariance of X and U is 0. But if I not able to defend that, I now say the covariance of Z and U is 0 and identify the model through that moment condition. But now I have to defend that Z is exogenous. And essentially, that's very difficult, right, in practice, to find a valid instrument. There are many papers using instrumental variables. I have many papers using instrumental variables, but it's always subject to this assumption. At least, and someone was asking me in the coffee break, a typical example of a perfect instrument is what? Huh? I don't listen, sir. You see, it's very difficult, a perfect instrument. It's a randomization, right? If you randomize something, then it's so. Suppose essentially you want to see the effect of the effect of S, right? S on W, as in this example. Well, we cannot randomize the level of education of the people, right? That's not feasible. Well, given what I said about frame entry, I don't know, but let's suppose it's not feasible. Still, what you can randomize is, for example, school vouchers that will affect the level of education of the people. So let's say that now set is the school voucher. So if the school voucher affects the education of the people, this is going to be satisfied. And then set is uncorrelated with the ability of the individuals because you randomize who got a voucher and who didn't, right? So that will be a perfect instrument. Yeah.
Isn't that the typical example of heterogeneity on treatment?
What?
Don't do like that. Don't do like that.
Will I not be much more likely to react on the voucher by increasing education if I expect high returns of education? And that's a classical heterogeneity of the treatment.
Yeah, but what
problem.
do you mean it's a classic heterogeneity?
Well, forget the classical. Is it a heterogeneity of the treatment effect?
But all treatments are heterogeneous. Remember how we define delta I is y1 minus y0 I, right?
To be specific,
so when treatment is not heterogeneous?
because they would be sorting on the gain in a way.
Huh?
They would be sorting on the gain in a sense, and much more likely to react by on the voucher by increasing my education if I expect that the additional education will actually benefit me.
Right. So let me go back to the previous lecture then. So I think the confusion here is this. So every individual has a delta I, right? That's okay.
It's very visible from far.
Huh?
The red pen isn't very visible from here. So if you have black or green or something.
Oh yeah, I had black before.
Okay.
No, I don't. Blue. Delta I, okay? So, one possibility is that we want to identify the expectation of this delta I, okay? That doesn't mean that there's no treatment heterogeneity, right? There's always treatment heterogeneity, but I just take the average, okay? And then I say, well, that's one parameter. We call it average treatment effect, okay? And now we define another parameter, delta I given treatment equals to 1, and we call average treatment effect on the treated, right? Again, there is heterogeneity in the population, but this is just one summary, right? So at the end, you're always going to get one average, right? Okay. So now, essentially, there is the instrument zeta I, right? That could be 0 and 1. You either get the voucher or not. And that could lead to DI also being, okay, so then you can have D of 0 also be 0 and 1, and DI of 1 also be 0 and 1, right? So that start to increase the possibilities. So suppose that we live in a world where among those that got 0, they didn't go the voucher, right? They essentially don't change their education level. But among those that get the voucher, some get, the ones that have a larger gain are more likely to take the voucher, okay? Well, by doing instrumental variables in this case, you recover the average treatment effect. There's no difference by the fact that it's instrumental variables, it's just that you recover that parameter. If now, there is this case where some of those that did not get voucher also increased their education level because of being an experiment, which, whatever, right? Right. So then you will recover an average of delta I given some subpopulation. Let's call that subpopulation compliers. For example, no, that's not the only parameter in the literature. But you see, it's not the issue of heterogeneity. Heterogeneity is present in every parameter. It's just what are you conditioned on in the when you do your estimator. Is something that you have to model. It will depend on what assumptions you make. And I'm not going to get into the details of all these papers because we're going to go beyond the hour. But for this just very introductory, I'm happy to think that we recover some version of an average effect by doing instrumental variable. Okay, you can get more subtle, but you have to specify down the assumptions of what's the relation between Z and D, okay? Good. Okay, panel data. Panel data, yeah. So let me again show all that here. So I would have been a much better professor before PowerPoint exists, because I hate PowerPoint. It's just so think about that. The question is saying, the reason I come in here is because my slide starts already in panel data. I want to go back to the problem of endogeneity cross-section. So this was the typical, I'm going to draw on the crime literature now, and people was trying to show that police reduce crime, right? More police reduce crime. That's, it might be, say, come on, obviously it's not true in Russia, but in the US people think it's true. So kind of, you know, there was think about this. Each of these curves is one city, okay? And in all the cities, I'm making this assumption that there is no heterogeneity. Police reduce crime in the same amount in all cities, right? That's, I don't need to make that assumption, but it simplifies the work. But cities are different in terms of how secure they are when there is no police. For example, this city, which it's in the US, it's not in Russia, right? Bethesda, where I live, even without police, you know, I often leave the door open and nothing happened. Nothing happened in terms that my computer is still there. So it's very secure. While there's others in St. Louis, for example, that are very insecure, right? So if you are the mayor of this city, you say, well, you know, how much police I can have? Well, I could try to get to 0. Probably it's not optimal. Let's put some police here. This guy is saying, well, you know, I can't live here. They're going to kill me. So let's go here. And so you'll have a data set. So now suppose you estimate this equation, crime on alpha 0 plus alpha 1 police plus epsilon I, you estimate exactly that police increase crime, right? And that's we know it's an endogeneity problem. But it's a particular case of an endogeneity problem. That's what I want to see. The endogeneity case because P being correlated with the intercept of the process that generates the data, which is this one. Sorry, this one. So the correlation is between P and mu. You see? It's with the intercept. And because it's with the intercept, obviously then in the cross-section is with the error term, because this error term, well, here I should use some other notation. Then let's call this U. In the cross-section, let's call U. This UI is going to be mu sub I it's going to be mu sub I minus alpha 0 plus epsilon I. That's going to be the error term. So what I'm saying is that all before we were saying, well, we have an endogeneity problem when the regressor is correlated with the error term. And that could be for many reasons, simultaneity, well, not many actually, 3 reasons. There's always only 3 reasons. Measurement error in the variable, simultaneity, or omitted variables, okay? So and then the solution for all these 3 is having an instrument. But having an instrument is difficult. You want to ask something? Yeah.
But in a way, this example sort of underlines why you need to do theoretical modeling, right? Because really the issue here is we kind of know what happens in theory, but really when you solve the model, you will pick this up straight away, right? So, you know, you're optimizing, and what you're theoretically would be confusing, and you will see this immediately, right? One is a marginal effect of police on crime, and the other one is the effect of a parameter at the optimum, right? And which is, and you know, it's, I think we shouldn't underestimate how important, even in these kind of relatively simple settings, it's worth writing a model down before doing empirical analysis.
I will never do econometric if there's no model. I don't see that it's always, so I'm not sure. Forgive me if I'm not taking your question exactly as you intended. The way I answer is that if you're saying don't run a regression without having a clear model, I agree 120%. If you say in the paper there has to be the model, I agree 0%. Because the model might have been done much better than you by Gary Becker with probability 4,000%. Right? It doesn't need to be a new model. It's problematic that you think that in every applied paper you're going to come out with a new model. Right? So. And still, a lot of what you're going to identify are departed from what the model predicts. Okay? So now the idea will be, okay, when panel, anyway, I'm trying to convey a much simpler idea. When panel data will solve the problem of endogeneity only when the problem of endogeneity is a correlation between your causing variable with an omitted variable that is time invariant. It's only a subset of the endogeneity problem, right? That's what I'm saying is the intercept. If the intercept is time invariant, right? Obviously, well, there is a slightly twist that maybe I can allow the intercept to move up and down, but at a ratio that is constant across cities, right? And that will be the period effect of the model. So essentially then, if we move to this model, say, where we know we are going to look about crime over time, we can exploit panel data. So let's think about this very, very simple case where we have only 2 periods, right? Now, because we have panel data, we can have 1 intercept per every city, which is mu I. And then we are going to have lambda t is the secular trend. It's the fact that essentially these things could be moving up and down. But now the idea is that I'm going to exploit the variability of police in each city. Okay? And now, see, this variability that's going to identify the model has to be random. Right? If it's predicted by your model, it's not going to identify the model in the panel context. You will have to go completely structural. Because suppose that when this city change the police, it is because they are seeing that the intercept is going down or up. Then it's exactly the same variability in the cross-section, and it doesn't identify. So what is going to identify the model is that there are random shocks, right, that are not predicted by the model. It's the random component that will identify the model. Because then you exploit only the within variability, and the within variability will always capture this negative slope. Let me show you this algebraic by essentially making this very simple case where I have 2 periods. In period 0, no one has police. In period 1, some cities still have 0 police, and some cities have 1 policeman, right? It's very, very simple just to... So let's take the change in crime, and then let's basically... Okay, I'm going to make one more assumption, that the expectation of epsilon, right, is 0 for every period of time. In every period of time, that's just a shock with mean 0, okay? So we take the change, then we condition on being a city that moved from no police to police, so the change in police is 1. So then that expectation is alpha 1 plus the change in lambda plus the change in the error term, given that the change in police is 1. So what's this expectation? What's the value of this expectation? Remember that epsilon has 0 mean in every period, right? So the expectation of the change in epsilon is 0, right? Because it's something that has 0 mean in every period. But that's not my question. My question is, what's the change in the expectation of epsilon given that we are looking at the cities that increase police, right? We don't know. We don't know. If all the increase in police is driven by the same logic, right, of the theoretical model, right, of the optimal allocation, it's not 0. It's likely to be positive. It's like when I see a positive shock to crime, I increase police. So then it's positive. Well, if it's positive, you'll see the model is not identified. I have to assume that it's 0, meaning that the change in police is uncorrelated to the change in crime in the cities that is unobservable. So that's basically the assumption. If that's not satisfied, panel data doesn't work. So, but let's make that assumption. Then, essentially, if we do the same for the cities, if that's true, then this is essentially the change. So notice this, this is what will be time series, right? Here is the change in the time series change in crime for those cities that increase police is the causal effect of police plus everything else, right? That's not what we want. We need the other cities, the cities that did not increase crime, and essentially there's a typo here. Here should be 0, and for those cities the change is 0. Sorry, the change in crime given the change in police is only everything else. And now if we do the diff in diff, we basically subtract the change in crime for the cities that police increase minus the change in crime for the cities where police did not increase. We get the alpha 1 plus everything else minus everything else is alpha 1. But that is true because we make this assumption that the change in epsilon given the change in p was 0. If not, if that's not true, then when we do the diff in diff, what we get is alpha 1 plus the change in epsilon for the cities that police increase minus the change in epsilon for the cities that police did not increase. And this is positive minus, and this has to be negative because the average is 0. So minus minus positive, you get a positive bias. Okay? So the key for the identification is the main thing of OLS. Let me put it in this way. When we want to identify causal effect in the OLS, in the cross section, right? When we look at the picture, we have cities with high crime and cities with low crime, and then we have to assume that police was uncorrelated with an observed component of crime in the cross section. We say no, that's not true. The police is optimally allocated looking at this unobserved component. So now we say, well, let's look at the movie instead of the picture. Let's look at the changes in crime as changes in police. Well, now we have to make the same assumption, that those changes in police are not correlated with the systematic changes in crime. Right? If they are correlated with systematic changes in crime, panel data doesn't solve the problem, because the endogeneity is coming from something that is time varying, which is epsilon. And I say, it only solves the problem when the endogeneity is coming from mu. Right? So in a way, panel will identify causal effects, but only when there is a cross-section endogeneity that doesn't translate over time. Over time, you get a kind of randomness variability. Okay. So this is because, let me put it in this way, in this perspective, right? When you want to identify a causal effect, you cannot do an experiment. Suppose you cannot do an experiment. You say, no, there's no way I can do an experiment. I have to do instrumental variables. It seems that where are you going to find an instrument? It's not that simple. It's not that everything could be an instrument. And then the easiest thing to think is, oh, let's do panel data. You know, it's always possible to collect panel data. Well, not always work. It's just not a matter of, okay, I have panel data, then I identify causal effect. You still need to satisfy this condition, which is called a strict exogeneity. Okay. And now, essentially, it requires that your causing variable P is uncorrelated with all the values of the error term. Contemporaneous, past, and future values of the error term has to be uncorrelated with the causing variable. So it's demanding. It's demanding. And the obvious way in which panel data fails, is not the only way, but it's the obvious way, is when essentially there are different secular trends, right? Which is a very common problem. So let me give you an absurd example. So So once I was asked to look at the paper that look at the privatization of water services into access to services in Ecuador, okay? So what the data was like this. So there were the places, so here is access, right? And here is, let's say, the time of privatization, T star, this is time, right? So after T star, they privatize, okay? So this is 100% access. So the paper concluded that once you privatize water, essentially that substantially reduce access to water. Okay, and it's possible. You can think, okay, they charge, exclude the poor, the state was subsidized, whatever. But that was not the story. I don't know what's the story. I don't know what's the true. I don't know what's the true story, and I don't know what's the answer to that question in that context, because the paper was completely uninformative. But essentially, the areas that privatized started with 95% access. And the areas that didn't started from 40%, right? So what's going to happen? This cannot go up. Right? It cannot go up. This essentially can go up, even if they go up 10%, right? It will conclude that privatization reduces access, right? Because in the privatized areas there's no increase, the others there's an increase. You are assuming counterfactual that the other, meaning that estimate what would have happened to the other areas if no privatization occurred, but that's not true. It's impossible that one is a counterfactual to the other. So think about this. Privatization brings the promise to accommodate difference in intercepts. That's the promise, right? That's what we say. It's all that endogeneity. But we have to be careful, because if these differences are very large, it's hard to believe that the changes will essentially satisfy the identifying assumption. There's going to be strict exogeneity. So in a way, panel data works, but you have to have something that was somehow comparable, in a comparable range where the assumption could be true. And ideally, you test that assumption, right? You test in a way that before the intervention, they were having the similar secular trends. So this will be the case where panel data works well. So you see, there's a difference in the intercept, but they have the same secular trends. And that you can test, right? You have data before, you test, and then one treatment shift one group, and essentially panel data is going to work well. This is the case where panel data is going to give you bias estimates, because they were not having the same secular trends, right? Yeah, that's not the only way panel data fail. There could be simultaneity, there could be measurement error. Measurement error gets exacerbated when you difference the data. But this is something that I see as pervasive, especially when you use many years of panel. And so, for example, the one group is growing at 1% more or less than the other group, and they'll accumulate over 10 years into a large difference. That is what you claim is the causal effect, right? That I see as the big dangers in panel data. But, you know, I still think, contrary to what many development economists are saying, a very useful technique, because there's a lot of panel data available, and it's something you can go and check and all that, right? So let me, I have 15 minutes. Let me talk about this regression to the mean problem in panel data very briefly, and And then, if I have time also, let me talk about the other paper. If not, bad luck. That's about also heterogeneous impacts in the sense of identifying them, okay? Identifying heterogeneous impact is something very interesting and it's doable. Interpreting them is very risky because there's hundreds of ways in which these populations differ. Okay. Okay, so essentially this is something I did with a co-author of me, Patrick McEwen from Wesley College. And this was an interesting paper because essentially there was kind of a puzzle in the literature because there were many conditional cash transfers that essentially give cash to the poor, and then the poor have to send their children to school, okay? And then Honduras did this program in the early 2000, like 2000, 99, 2000, 2001, and it was evaluated. It was evaluated, and the team that evaluated, and it had an extremely nice design that was not used at all in the evaluation. What was the very nice design? It's so nice that I'm still writing about this, several papers. So suppose you order municipalities in terms of poverty, and they were able to do that. With a very good indicator of poverty. They have anthropometric data for all first graders in the country, right? So they rank the municipalities by this indicator, and they say, well, we are going to define some threshold, P star, and all the municipalities below the threshold will be treated. No, will be treated. Will be eligible for treatment. Will be eligible for treatment. And all those above will not. Okay? You follow, right? But they did more than that. Then they stratify in 5 stratums. 1, 2, 3, 4, 5, right? And so these are very, very poor, all are poor, but less poor, less poor, less poor. And everywhere they have treatment and control, treatment and control, treatment and control. So in a way, you have 5 different experiments, right? And you can then look at the heterogeneous effects by just estimating the effect here, 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 okay? Right? So I write the model, because it's not obvious where you're going to find the larger effects, and it depends a bit on the concavity of the utility function and the convexity of the wage function, right? And the wage function will vary because if you think that essentially these are children that could go to work in the farm or go to school, the money they receive as a transfer will affect consumption, but also the opportunity cost will vary across a strata because essentially the anthropometrics of the children are worse and worse, and you could imagine the productivity is different. So it's not obvious what's going to happen. But under some concavity assumptions of the utility function, you can predict that the effect's going to be monotonically decreasing. Okay? That's the case where I think the model has to be in the paper. The editor thinks I should drop it, so it's not anymore. But anyway, so the original evaluation did not look at the effect stratum by stratum, because they didn't have enough sample size, right? They collected data before and collected data after in a typical evaluation way, but they didn't have enough sample size for estimating 5 different effects. And then it led to a puzzle that also the average effect on school enrollment was very low, 3%, right? When they do diff in diff, right? When they do diff in diff, when they just compare the means after, they get 8%, right? 8%. So why that was happening? Because education, school enrollment was unbalanced before treatment, okay? It was unbalanced before treatment. And so they say, well, if it's unbalanced, then we do better by doing diff in diff. And I say, no, you do better by ignoring the imbalance and just comparing the means. So let me ask you, when do you think an imbalance in an experiment justifies a diff in diff and one is not? I never know about this problem until I did this paper, right? But the panel literature will tell you the answer, right? When panel data solve the problem? When there is a difference in the intercept that is permanent. So the imbalance, you have to get convinced that it's not something that just happened that period, right? Suppose it was just a shock in that period that will not occur in the next period, then the worst you can do is diff in diff. You should ignore the fact that you have one variable imbalance and say, well, that was just it's the random noise. Every time I randomize, so out of 100 variables, I have 1 or 2 imbalance. It was an outcome, whatever. It could have been a control. The fact was that nothing else was unbalanced. And what is worse, we know what it was unbalanced. They collect the data for the control and treatment in an asynchronic way that did not overlap with the school year. Right? So it was something that but interesting. Then I say the interesting part is not all this discussion. The interesting part is to look at this effect, this effect, this effect, this and this. And I don't need to have pre-treatment data, and I have the census. And in the census, I have millions of observations I can use just after the treatment, so I can look at the effect. So if you take the census and you do the average of this, what do you find? Exactly 8%. Exactly 8%. Now, if you do it strata by strata, you find 30%, 20%, 0, 0, 0. That's very interesting because there is a heterogeneous effect. It is basically, as the model predicts, effects are much larger at the bottom. But also it has a very interesting lesson that we discussed in the paper. Suppose you don't have an experiment, right? Imagine that the government could have done something different. Could have said, look, all the municipalities that are below this threshold, they will be treated. And all above, they will be untreated. How will have a researcher evaluated the program using a regression discontinuity design? In a regression discontinuity design, essentially the running variable is the anthropometric, right? And they will have look at municipalities around the cutoff. We did that in the paper. What we have, regression discontinuity work perfectly. We find 0 effect, right? But that 0 effect is the true effect at the cutoff point. It's just not interesting because all the effect is among the poorer, right? Well, fine. I think I have to stop, but experiments are very useful to look at heterogeneity, but I think the right way to do is to stratify on subgroup, because If not, then essentially you just randomize, and then all the heterogeneity came by people throwing interactions with the treatment. And as I say, so you interact with having a radio. But having a radio is correlated with another 100 things, right? So it is not the radio, and it's tricky because you can do 100 interactions, you'll find 5 that are significant, you say, okay, this is heterogeneity here, right? And there's a lot of experiments like that in a way they find effects for one group and not other, and then there is an unexposed rationalization. And again, I might have papers like that myself. I'm not advocating, I'm just saying that this thing was an extremely nice feature that it was really good that they did it that way. I was surprised that they did it that way, and they didn't collect data to use that design. And we were able to publish a paper like 15 years after the experiment, just because we revisited the experiment in a way that no one used it before, right? Well, anyway, I'll stop here, and we can keep talking during the afternoon or tomorrow about stuff you are interested in. Okay?
Yeah, thank you very much.